So we're doing smaller segments so I can make sure that these get put onto Moodle easily. It'll just be several segments till we get to kind of the full class period, but I'll try to include all the normal information I would in a chalk talk. And we'll leave lecture for discussion questions and perhaps to augment the lecture material. I'll try to have a pad available or a chalkboard that I can go through questions either on the chalkboard or a touchpad. We've been talking in chapter 18 about alpha beta unsaturated carbonyls. Last segment, I told you about 1,2 additions. What I want to focus on this round is talk about 1,4 additions to alpha beta unsaturated carbonyls. The things that add 1,4, these are things that add to the carbon of the terminal carbon of the alkene. And these are things that generally are soft nucleophiles that have not as much concentrated negative charge or it's delocalized negative charge. These things tend to prefer to react here rather than where there is more partial positive charge at the carbonyl carbon. So the term that's used is a soft nucleophile. Electron density is delocalized or spread out or not as focused or concentrated. These things tend to react here. I have a list of them on the board. Things like alcohols, water, amines, cyanide. We'll talk about organocuprates, enolates. These are all things that add 1,4 to alpha beta unsaturated carbonyls. So for example, again, these are under equilibrium conditions. If we just add water, you get mostly just the alpha beta unsaturated carbonyl. But if you add a base, such as hydroxide, these reactions go much faster. So in this case, my hydroxide will do a 1,4 addition. What does that look like? It means that at this carbon, the beta carbon of my alpha beta unsaturated carbonyl, I'm actually making a bond between that carbon and the hydroxide so that I end up with this product, right? And so this is technically a 1,4 addition, looks like a 1,2 addition because I'm adding here, I protonate here, and then tautomerize back to the carbonyl, right? So water, for example, will add 1,4. Another example of this would be an amine. So amines also add 1,4. It's thermodynamically more stable than the hemiaminal that would relate from initial addition to the carbonyl. And so as a result, the preference is to favor the 1,4 addition, right, which looks like this, right? So we end up with the amine actually making a bond to that beta carbon of my alpha beta unsaturated carbonyl. And this is a good way to install nitrogen. From a retrosynthesis, this is a little harder to see, right? The bond that we're making is this one to the beta carbon. Okay, so again, thinking that these came from alpha beta unsaturated carbonyls. If we think about the mechanism for this, whether I use hydroxide or the amine, these are both going to look pretty similar from a mechanism standpoint. My hydroxide in this case is a strong enough base to add directly, but we're still under equilibrium conditions. The end result of the addition is to make an enolate here. And again, this enolate has some negative charge at the oxygen as well as at the alpha carbon. And that's where we will protonate, right, with water. And the end result is the 1,4 addition. We end up here. So again, it'll be similar for amines. And again, alcohols, amines, water, all do this 1,4 type addition. Mechanisms are still under equilibrium conditions, right? We can also do this with what we saw with additions, 1,2 additions to carbonyls, is that given an alpha beta unsaturated carbonyl in the presence of, so alpha beta unsaturated carbonyl, in the presence of KCN and catalytic amount of HCl, right? What we see is 1,4 addition to that carbonyl, right? So what does that look like? It means that my carbonyl stays intact, and where I added was to the beta carbon. So again, reorienting, I add to the beta carbon. So again, not a bad idea to number, or at least indicated alpha and beta. And again, these go pretty well, 67% yield. So I've added a carbon, right, beta, to where I have a carbonyl. Again, this is the bond that I'm making from a retrosynthesis standpoint. From a mechanism standpoint, since in this case, we do have a catalytic amount of acid around, these likely protonate first. So I'm going to protonate at the carbonyl. That'll even put a little more partial positive charge on the beta carbon here. So that now my cyanide can act as a nucleophile. And we get to here. Right, so here's my alpha carbon, here's my beta carbon. I recognize this as an enol, right? I'm not going to draw out the full mechanism for that, but the enol will tautomerize back to the keto form. And again, this is adding to the beta carbon as a result. So I didn't draw out the full mechanism for tautomerization, but we have seen that before under acidic conditions as a result. Okay. As I mentioned last round, right, lithium, organolithium reagents, specifically add 1,2. Organometallic reagents such as Grignards give mixed results. So addition of this to an alpha beta unsaturated carbonyl actually gives both 1,2 and 1,4 addition. So as a result, it's generally best not to use Grignard reagents, in particular with alpha beta unsaturated carbonyls. Instead, if I want to add or make a carbon-carbon bond beta to an alpha beta unsaturated carbonyl, I use something that's known as an organocuprate. These are considered soft nucleophiles, and they're made by the reaction of an organolithium with copper iodide. So if I mix 2 methyl lithiums and a copper iodide, the reagent that I get out is the CH32 CuLi. This is known as an organocuprate. It reacts like a soft nucleophile, and for alpha beta unsaturated carbonyls, it adds 1,4. So I indicate how these are made because these come from lithium reagents, which means I can't have any acidic pieces in my R group here because the lithium reagent will just deprotonate that. So how these are used in context of alpha beta unsaturated carbonyls, okay, so I've got some kind of R group here, is the R group is what's getting transferred to the carbonyl, right? To the alpha beta unsaturated carbonyl, and the intermediate is actually an enolate. So addition of this to an alpha beta unsaturated carbonyl generates an enolate, which I could capture with a second electrophile. And so one of the things that's useful about organocuprates is I could add carbon-carbon bonds at both the beta position and the alpha position to the alpha-beta unsaturated carbonyl as a result. So if we want to look at a specific example, or actually let's do a mechanism first. If we do a mechanism for this, what we see using a generic R group, so here's my lithium, copper, right, is it's this, one of the copper alkyl group bonds, right, this is acting as a nucleophile here. That's going to end up generating enolate. So if I draw this way, that's going to generate enolate here. So that now if I add in a good, again, this is SN2, so now if I add in a good SN2 substrate, thinking about the limitations for SN2, right, I can get to here. So organocuprates are used to add 1,4 to alpha, beta, unsaturated carbonyls. Okay, so let's do 2 specific examples so you can see what this looks like. Okay, so for example, here's my carbonyl, and I'll make this colored. So if I do CH3, 2, CuOI, right? And just follow that up with H+ and water, that's just going to protonate the intermediate enolate. And so the end result of that, my carbonyl stays intact, and at the beta carbon is where I'm going to add that R group. So in this case, I'm going to add that to this position. So this would be the result. In this case, I think this one's about 40% yield or so. 40 to 50% yield isn't uncommon, but I have made a carbon-carbon bond, beta, right? Beta to my carbonyl. So from a retrosynthesis standpoint, we have to keep in mind that this could be made here from an alpha-beta unsaturated carbonyl. One more example, right? So if I do this, so only one of the R groups is transferred from the organocuprate, and then we're going to follow this up with CH3I. Okay, so end result for this. This is going to add to the beta position, right? So this is going to add down here, and that's going to add a propyl group, 3 carbons here. This is going to intercept that intermediate enolate, which is going to put a group here. Now we do see some stereochemistry preference, mostly from a relative standpoint, right? So what we see is this is the favored product from a relative chemistry standpoint over the cis, right? This one is favored about 4 to 1 and about 84% yield overall. And so again, this is a great way to make carbon-carbon bonds, beta to a carbonyl, and we're using a cuprate to do that.